In this video, we'll talk about methods for selection in genetic algorithms. In other words, how do we choose parents and survivors in this loop? Let's start by talking about parent selection. Here are some important notes before we begin. Number one, parent selection is based on the fitness of individuals. Individuals that are more fit should be more likely to be parents more often. And then individuals can be selected as parents more than one time in a given generation. In other words, the same individual can have more than one kid. The first type of parent selection is called fitness proportional selection, or FPS for short. Here's the equation that governs FPS. Let's identify what each of these variables means. So P sub I stands for the probability of becoming a parent. This will be a number between 0 and 1. F sub I, or F sub j, is referring to the fitness of a given individual. In this particular case, this would be the fitness of the jth individual. And these individuals are coming from our population, so mu governs how big the population is, or the population size. So to summarize, the probability of any individual in the population getting selected to be a parent is essentially based on the ratio of that individual's fitness relative to the sum of all of the fitnesses in the population. There are a few challenges to this approach. Number one is premature convergence due to superior individuals. In other words, there might be some individuals whose fitness dominates the sum of the fitness in that population, and those individuals are going to be so likely to become a parent that maybe we only have a few parents that are generating all the children, so we're prematurely converging to essentially the family of that solution, even though that might not be optimal overall. Also, there's low selection pressure if you have individuals with similar fitness values, even if one of them is clearly a better solution than the others. And then third, the transposition of fitness values can end up yielding drastically different results. Let me show you what I mean by that. So here we've got a plot of fitness for specific individuals in our population, and I've got two different populations. The one in orange has just been transposed up, so we've added to every individual a fixed amount of fitness, but you can see that the trend relative to other individuals in the population is the same. So if we look at three individuals in particular identified by the green circles, let's look at what their probabilities are according to FPS. So as an example, this individual down at the bottom here is identified by the probability of this slice of the pie. And you can see in the case of the blue, it is significantly lower than the probability for that same individual in the orange. So transposing the fitness made a big impact on the overall probability of being selected as parents. There's really two solutions to this that are used commonly. The first solution is called windowing. The idea of windowing is that we scale the fitness of any individual either based on the current generation or maybe like the minimum value of the population for the last 5 generations. And if we do that kind of scaling or take that window of time with which all fitness is relative, then the FPS equation here will be somewhat consistent for different generations of populations. The second, which is also a variant of windowing, is called sigma scaling. So this is a specific technique that was discovered by researchers that essentially takes into account the mean and standard deviation of the current population to normalize the fitness values in each generation so that FPS is more consistent, again, from one generation to the next. You don't need to know the details of these solutions, just know that by adjusting the relative scale of fitness values, we can address some of the challenges of computing probabilities using FPS. The second way that we can compute probabilities for parent selection is by ranking selection. So here's the corresponding equation. P sub I still stands for the same term. It's the probability of the ith individual becoming a parent, and that should be a number between 0 and 1. Mu is still the size of the population. I is the index of an individual in the population. But now we have a new design parameter. That design parameter is S, a factor that ranges from 1.0 up to 2.0. So inclusive on the 2.0 side, exclusive on the 1.0 side. It's also worth noting that I here is going to be varying from 0 up to mu minus 1. So I'm assuming we have 0 indexing going on. And in particular, we're assuming that the population is going to be sorted from worst to best. So the best population in this particular instance is going to be at the mu minus 1 position. I'll tell you, in practice, when we do genetic algorithms, that's often not the case. I like to think of the individual at index 0 as being the best, but just recognize that this equation only holds if I have that kind of sorting from worst to best. So for a simple population where we have 3 individuals, I'm going to show the probabilities and how they vary with that design parameter S. So I've got 2 columns here where S is equal to 2 and S is equal to 1.5. And I've shown how the equation for ranking selection simplifies for both of those 2 cases, noting that this only is true when mu is 3 in particular. So if you increase the size of the population, the probabilities will change a little bit. But for this particular example, the worst individual when S is 2 is going to have a probability of 0. The next will have a probability of 1/3, and then the best one will have a probability of 2/3. In the case where S is lowered to 1.5, you'll see that it gives the worst individual more of a chance, so 1 out of 6. The second individual is 1 out of 3, and the third individual, the best one, still has the highest probability of 1/2. And in all of these cases, you'll note that summing the probabilities as we would expect, it should be equal to 1 in both scenarios. And that's true no matter how big the population is. One of the challenges with this particular approach is that we have limited selection pressure due to mapping of linear rank. In other words, we actually don't know or don't care in ranking selection how different the fitness values are. All we care about is where you are in the order of ranking in that population. Now, I want to clarify that the 2 things that I just talked about as types of parent selection, those are ways to compute probabilities that individuals should become parents. But how do we actually implement this in code? In other words, what are the methods for picking those parents? That's what we're going to talk about now. And the first of these methods is just a roulette wheel. So the idea here is that we're going to spin a 1-armed wheel lambda times. And lambda in this particular instance is referring to the number of parents, but also the number of offspring or children. Typically, those 2 numbers are going to be the same. In the literature, lambda actually more often refers to number of offspring, but again, those are usually the same as the number of parents. Now, the key here is that the sizes of the pockets in the roulette wheel, those are going to be proportional to the probabilities of each individual being selected as a parent. So here's what that code might look like. And I'll note that when I use the variables m and n, this would be replacing mu and lambda. So the size of the parent population, that's mu, but I'm just going to use simpler variable names in the code. So I'm saying I have 100 individuals in the population, but the number of offspring and therefore the number of parents is going to be 100 in this case. Those numbers don't always have to be the same. You could generate more parents or fewer parents than offspring. It partially depends on how you're going to do survivor selection. Next, you'll notice that I have a variable called prob for probability, and it's just equal to a question mark. And the reason it's a question mark here is because I don't really know or care how you're coming up with that. Somehow, probability is going to be computed probably via FPS or the ranking selection that we talked about. And then we're going to use that probability to make a random choice n times from that m-sized population. So really simple line of code that does this. Conceptually, here's how that is working. So perhaps I have this wheel, right, 360 degrees, Every slice in this wheel refers to the probability of a particular individual in the population. So if we count the number here of pockets, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So it appears that mu is going to be equal to 9 in this particular case. And then when I say that it's one-armed, what I mean is that I've got essentially an arm attached to the center of this wheel, and I'm going to spin the arm, right? And when I spin the arm, it's like The Price is Right or Wheel of Fortune or something, right? You spin it and it will land in a certain slot. The slot that it lands on is the parent that gets selected. So you can see how probabilities increase or decrease based on the fitness values of those individuals. We're going to spin that wheel as many times as we need parents. So in this case, that would be lambda or n in the particular variable set that I'm using for the code. Now, the second type of method for implementing parent selection is called stochastic universal sampling, or SUS for short, SUS. Very similar concept to the roulette wheel, except this time we have a lambda-armed wheel, and we're going to spin that one time. The pockets of the wheel are still proportional to probabilities of each individual. So we have the same kinds of variables, and the probability, again, is coming either from FPS or ranking selection. But let me draw what this diagram looks like. So we've got our probability distribution for each of the individuals in our population. I think I've drawn more individuals in this particular example. But now, instead of a singular arm on the wheel, we're going to have evenly spaced lambda arms on the wheel. Now what I'm going to do is I'm going to spin this entire 10-armed contraption on the wheel, right? So I spin this, and each of those 10 arms is going to land in one of the buckets. So every time an arm is in that particular bucket, that individual becomes a parent. So it appears here that the most fit individual in this particular population is getting picked multiple times, right? It looks like this individual gets picked 3 times. The probability still increases your chance. As the probability increases, it increases your chance of becoming a parent. The thing that's interesting about this version versus the roulette wheel is that I think it distributes the parents a little bit more. So hopefully it's clear to see that in this case, that most fit individual, it couldn't become a parent 10 times. That's not possible because the arms of the wheel are spaced out evenly. In the simple roulette wheel, where we spun the one-armed wheel lambda times, in theory, it's possible that the same individual could become a parent all the time. So that's better conceptually, but as you can see here from this note, I haven't even given you the code, and it's because it's more complicated than just one line. So there's a nice trade-off there between, do I want a better outcome where I have more diversity of parents, but harder code, or am I willing to sacrifice having the same individual be a parent perhaps too many times, and yet the code is going to be much simpler? Lastly, we come to my favorite method for implementing parent selection because it's rather straightforward, and that's called tournament selection. So the idea here is that we're going to pick k individuals. Note that k is not the number of parents we want. K is the size of the tournament. So we're going to have a tournament for each parent, and the winner of that tournament, in other words, the individual that becomes the parent, is simply the one that has the best fitness from those random individuals. Here's what the code looks like. So as a reminder, mu, or m here, is the size of our parent population. These are the individuals that could be picked as parents. N, or lambda, is going to be the number of offspring or parents that we want. And I'm assuming again here that number of parents will be equal to the number of offspring. K is going to be our tournament size. That refers to how big of a tournament do we want. I'm setting it equal to 2 here. In other words, when I randomly pick k individuals for each of the n parents that I want, that randomly come from a population of size m, the winner is going to be the better of those 2 random individuals. This line of code before the .min axis part, what this is doing is it's generating a population or a new array that has a size, in this particular instance, of 2 by n, and then we're going to pick like the better of the 2 in each of those rows to become the actual parents. That will be a 1 by n array. And it's a simple NumPy function from the random library called randint. The min axis equals 1 here is just the way to say which is the better of the two. So you'll notice, and I'll make a note here, that I'm assuming lower index means more fit. If you wanted to assume that the lower index meant worst fitness, like we did with the ranking selection equation, instead of taking the min, we would simply take the max here. But we would still want it to be on axis 1. So let me show you an example of what that tournament might look like. I've got my population indices. So this isn't the individuals or the genotypes themselves, but if I've got 10 individuals, then the possible indices are 0 through 9. So that's what I'm showing in red. I'm setting up the tournament array, and just for spacing purposes on the slide, I'm gonna rotate it so that there's 2 rows and there would be n columns here. But here are some sample random indices that I might have for the tournaments. And the number of tournaments would be based on the number of children here. So according to the code, there would be 10 columns. The way that the tournament is won is by looking at which individual has the better fitness or the lower index. So sometimes an individual will be in a tournament that it wins. Sometimes it will be in a tournament that it loses. But those indices will then be passed later on in the algorithm as the parents that need to cross over and subsequently mutate. And perhaps if you were taking 2 parents to make 2 children, then we would simply pair these up. So 1 and 0 would become the first parents of the first 2 children, 0 and 8 would become the next parents of the next 2, 5 and 3, 4, and so on and so forth. So again, this is just a really straightforward, simple way to generate indices of parents from our population that still is based on the fitness, but it's not based on the raw fitness value, so it may have some limited selection pressure. Instead, it's just based on the ranking of that individual within that population. In my experience, this is the easiest of the approaches to use, and so it's a very common one. K doesn't have to be equal to 2. In fact, I'll base K largely on the size of the population. So the bigger the population, perhaps the bigger the K. Normal values of K would be 2, 5, 10. We're not going to make K like 100, because if you think about it, if we randomly select 100 individuals, then that means that the worst 99 individuals in the population will never win the tournament, right? You should think about that. How many individuals will never become parents based on the value of K in our tournament selection? That would be a good exam question. All right, let's move on to the other part of selection, which comes at the end of the loop for each generation of our GA, and that is survivor selection. The first of the 2 approaches is called age-based replacement. We generally identify that with this notation where we say mu comma lambda. So that means that we're going to replace all of our parent population with our children. Typically, we will then generate the same number of children as our parents because we don't want the population size to grow. Now, you can do age-based replacement where lambda is greater than mu. In that case, you would simply take the best or the most fit of the lambda children, but we're still getting rid of all of the parent population. The idea here is that highly fit individuals, they would have become parents at least one time, and then those parents would breed children that potentially are useful in getting closer to the optimal solution. The second type of survivor selection is called fitness-based replacement. So this is where in the notation we say mu plus lambda. So we're going to include, for survival of the fittest, both the parent population and our children. And we're only going to replace the parent population that's weaker than the offspring. Let me depict how this plays out in practice. We've got the initial population that has mu number of rows. The number of columns here would be based on the genotype, how many genes there are. And then we're going to generate parents and children based on lambda. Okay, and again, I'm assuming that the number of parents is equal to the number of children. Technically, that's not required, but it's very common. Now, how did those parents get generated? That parent population simply took or extracted certain individuals from the original population to be those parents. And sometimes the same individual got to be a parent multiple times based on how fit they might have been. So those are just extracting rows from the original population to become parents. The parents cross over to make the children then mutate on their own. When we talk about fitness-based replacement, normally we're not talking about combining the orange and the blue. Typically, we'd be talking about combining the red and the blue. So we take our original population that has not crossed over, not been mutated, and we compare it to our children that came from parents in that population. And now we're going to resort this combined group on fitness and only keep the top mu individuals. Again, the size of a population from one generation to the next is generally not changing in a genetic algorithm. So in this case, we might have lambda that's much smaller than mu. Maybe if mu is 1,000, maybe lambda would be 500, in which case we now have 1,500 individuals to determine who survives. So that guarantees some of the parents will live on. Or we could make lambda really, really large. We could make it double the size of mu, and then we've got essentially 3 times our original population to choose from on the next generation. In any case, it is the fitness of the individuals that dictates whether or not they survive. Survival of the fittest is the key principle of genetic algorithms. Okay, the last note we need to make is for a couple special techniques involving survivor selection, and the first is called elitism. So recall that the idea here is that we want to allow a specific number of the best individuals to always survive. If we do age-based replacement, for instance, that by itself will discard all of the good solutions from our original population. We'd like to probably keep at least the top 1 or 2 of those solutions so that they can live on and potentially be the best at the end of the day. Elitism is what allows us to do that. Now you'll note that I've said that it's not necessarily sorted yet, and that's because the elite on one generation may not be the elite on the next one. So when we sort, maybe some of these green individuals, they might move down when we sort by fitness, and then they're no longer elite to live on, to be guaranteed to live on in the future generations. Another technique is called genitor, and the idea of genitor is to replace the worst lambda individuals in the parent population. So it's almost looking at it from the opposite side, where instead of keeping the best, we're saying we want to guarantee to replace the worst. So it's very similar to elitism, but slightly different in practice, replacing the worst as opposed to guaranteeing that we keep the best. And that's all there is to it for selection in genetic algorithms. Thanks for watching.